please.
Thank you very much. Okay. Thank you, the organizers, for giving me the opportunity to present this work. This work is based on a paper by Paolo Di Vecchia, Carlo Heisenberg, Rodolfo Russo, and myself, which appeared recently, and there will be perhaps a couple of papers to appear next. And some of the material will also be discussed in a somewhat complementary talk by Carlo. Let me start by explaining, if you want, the title of the talk. It's related to a 2-year-old puzzle. 3 years ago, about 3 years ago, Thibaut Damour suggested that useful input for the effective one-potential could be obtained from the high energy or ultra-relativistic regime of gravitational scattering, which was discussed, among others, by Amati, Ciafaloni, and myself since the late 80s. Now, that proposal made a lot of sense because if you could also use ultra-relativistic limits, then the so-called post-Minkowskian or loop expansion could be anchored to two limiting cases: the much-studied small velocity or post-Newtonian expansion on the one hand, and the ultra-relativistic limit on the other. And I should emphasize that both limits are classical. Now, last year, in a paper in January last year, and a longer one in August, there was an impressive calculation by Bern et al. I would not go through the list of names, too long. And this led to the first complete, I put complete, quote unquote, because of reasons that I will explain later, a complete 3 p.m. result. This was done in general relativity for two massive scalars. This result was announced already at the QCD Mid-Gravity meeting in Stockholm in December, exactly 2 years ago. That result was checked to be consistent up to 5 post-Newtonian order, and later also to 6 post-Newtonian order, again, in quotation marks for reasons that will become clear. However, that result presented a puzzle. The puzzle was that the high energy or just the massless limit of the Bern et al. Result exhibited a logarithmic divergence in contrast with a perfectly finite result by Amati et al. In 1990. Note that gravity is supposedly free from mass divergences or collinear divergences, and that gave rise to quite a lot of controversy, which I will not try to summarize. Now, furthermore, both the massless limit of ACV 90 and the Bern et al. Log enhancement at large S over m square have been checked by the papers which are, written there, have been claimed and in many cases checked to be universal. And yet they look to be mutually incompatible. So the prevailing attitude till a few months ago was that the limits, when you take the momentum transfer smaller than the mass, all much smaller than the energy, or the opposite order of limit for the mass and the transverse momentum, transferred momentum, were unrelated. In other words, the feeling was that post-Newtonian and ultra-relativistic don't meet or don't talk to each other. However, the solution of the puzzle turned out to be quite different, and that's basically the topic of this talk. Now, this is the outline. There will be a very, very quick reminder of the gravitational eikonal approach that we will follow. Then a part which will have to do with sharpening the puzzle, which I just outlined. Then there will be a section on massive n=8 supergravity calculations. And on all these parts, I will go pretty quickly, also using the fact that tomorrow Carlo is going to cover some of the same material. And then there are some new results on which I hope to have time um, to give some information. So in my slides, there will be more than I will be able to explain, but I decided to leave the material in the slides for people who want to look at them, offline later on. So first of all, the gravitational eikonal approach, in just 2 words, it was started in the late 80s. It's an eikonal resummation in impact parameter space, which restores unitarity by converting a partial wave unitarity violating amplitude into a large phase. So the S matrix in impact parameter space takes the familiar form of e to the 2I delta, and this phase, this eikonal phase 2 delta, takes the form of an action divided by the Planck constant. And if that ratio is much bigger than 1, you can recover a classical limit. In fact, when you go back from B space to Q space, one recovers general relativity expectations and occasionally derives some new interesting results through saddle point approximations. You can find the review in some lecture notes of mine. Now, sharpening the puzzle. So this consists on 2 parts. First, extending the old, 30 years old argument by ACV. So let me sketch how that argument goes. Basically, we made it more rigorous and more general, for instance, to cover also the limit in which the momentum transfer is smaller than the mass, whereas the old result referred to the strictly massless case. So we use general properties of the scattering amplitude in the high energy limit. The basic properties are real analyticity, it's written there, crossing symmetry, because we take a process which has SU crossing symmetry, and some knowledge of the asymptotic behavior in order to write suitably subtracted fixed T dispersion relations. This is all standard things. Now, from those, we get information on the high energy limit of the ratio of the real to the imaginary part of the scattering amplitude, in analogy with what is done a lot in high energy soft hadronic physics. It was very popular in the 70s. It's now again popular with the new LHC data. And I think it's also, I'm pretty sure actually, it's recent by Caron Huo et al. And as far as I understand, he will give a talk which will use those concepts as well later today. So the typical results, if we know that the imaginary part of the amplitude goes with some power of S times some power of log of S, so P will be the power of log S, and we can easily figure out from dimensional considerations, then we can get a handle on these ratios of real to imaginary part. You crank the machine, you have to look into the paper to see the details, and you arrive at a very interesting relation between the real part of the phase shift of the eikonal and the imaginary part. Here 2 means 2 loops. And this thing, you see, depends quite crucially on this number P over here. P appears here, here, and also here. And you see that for generic P, for instance, for P equal to, let's say, we are left with a non-universal piece because this imaginary delta 1 turns out to be dependent, for instance, on the number of supersymmetries in the theory. But also, and more seriously, if P is not 1, this ratio of imaginary delta 2 over log s diverges at large s, okay? Say if p is bigger than 1. And uh, and also, since neither delta 1 nor delta 0 have log s dependencies, it will turn out that real delta 2 will not have a finite ultra-relativistic limit. So this general consideration show very clearly how the puzzle arises from the fact that in the Bern et al. Calculation, p is equal to 2. So this gives a logarithmically divergent real part and a non-universal result as well. Now, I just copied the formula there. On the contrary, if p is equal to 1, then real delta 2 does not depend on this non-universal im delta 1 because p is equal to 1, and approaches a finite ultra-relativistic limit because this ratio goes to a finite number. And in fact, the whole relation simplifies like this. And the logarithmically growing term in im delta 2 has an infrared divergence, which, however, is precisely canceled by this delta 0 contribution. And eventually, you find a nice finite result for real delta 2. So these general arguments already sharpen the puzzle, but you still have to compute this imaginary delta 2 to see really the origin of the puzzle. So we revisited the three-particle unitarity cut because im delta 2 is precisely related to the imaginary part of the elastic amplitude at 2 loop. I mean, sorry, more specifically to the three-particle unitarity cut. And this was done again in ACV 90 for m equals 0, and we have redone the whole calculation for generic q squared over m squared at high energy. I will skip the details of the calculation and just tell you that the final result exhibits precisely what I was telling you about. It goes with a single power of log s, so my parameter p is equal to 1. It has indeed an infrared divergence, but this is nicely canceled against this delta 0 contribution, and at the end one recovers the finite ACV result at epsilon equals 0, and this is the ACV result. So as a result of this quite general argument plus this explicit calculation, we saw that the ACV, the puzzle between these two results had become more and more puzzling, if you want. So we then decided to compute the full amplitude in n equal 8 supergravity with massive external state introduced via KK compactification, and we picked up a particular value of this angle between branes, phi over 2. Now we went to arbitrary energy, so from deep non-relativistic to deep ultra-relativistic. We used the method of integration by parts plus differential equation, quite standard, but included contributions from the full soft, namely potential plus radiation region. It is known, for instance, see the talk of Ruth yesterday, that including only the potential region implies loss of crossing symmetry and also of manifest Lorentz invariance, and these are both crucial in the ACV 90 argument. While if we keep the full soft region, we restore crossing symmetry and Lorentz invariance. So, and we found that at high energy, the sum of planar and non-planar boxes gives a contribution which is of the same order as the one coming from the so-called H topology. As a result, the log square terms in imaginary A2 cancel in the sum between the H topology and the planar and non-planar boxes. And, and so because of the general argument, once the log square terms cancel in imaginary A2, the single log S term cancels in the real part of A2, or in the
Gabriele, you have
real.
5 more minutes.
Okay. So the final result confirms asymptotically the ACV 90 and extended to arbitrary kinematics. It was also later confirmed by a different method by this author, Herman Para-Martinez, and Zeng. So I will give it later and refer to Carlos' talk for more details on that. Now, the real analytic crossing symmetric form, I will go quickly on this. We have seen the importance of analyticity and crossing in relating different quantities and simplifying calculations. So it is interesting and useful to recast our 3 p.m. results, I repeat, in n equal 8 supergravity, in an explicitly analytic and crossing symmetric form. Now, because of time, I will only flash the formula. So I will only flash the fact that, for instance, the two-loop amplitude now at arbitrary kinematics can be written in an explicitly crossing symmetric form, because if you want the bar variable at the cross of the unbarred variables, and you see that the expressions we got are nicely analytic, have all the right branch cuts from U channel, S channel intermediate states, and they're crossing symmetric. And eventually we get this, interesting result where I want to emphasize that besides a standard 2pn contribution, post-Newtonian contribution, we got on top 2 half-integer pn contributions. Separately, they are 1/2 pn, but their sum is 3/2 pn. And now here comes the important point. When we stare at these new terms, we realize that because of analyticity, the real and imaginary parts of these contributions to imaginary real delta 2 appear in a very well-defined contribution. And in particular, let me emphasize that the imaginary part has an infrared divergence, I over minus epsilon, and the real part which is given by pi. So there is a nice connection between this real part and the imaginary part. And this is extremely interesting because it gives a new intriguing connection between soft theorems and the so-called radiative reaction contribution to the 3 p.m. initial phase. So this is the, if you have to, remember one formula of this talk, I suggest to remember this one. The radiation reaction contribution to the phase shift or to the eikonal, it's related to the imaginary contribution as epsilon goes to 0, and this is well known that it gets related to the so-called zero frequency limit of the spectrum of energy radiation in the process. And this, for instance, has been checked at low velocities in a near threshold and fits very nicely with a Kovacs and Thorne limit. Now, so this I will not discuss. I think they will be presented in any case by Carlos' talk. And let me only finish with the connection with Damour's work. I was hoping that Thibault would give a talk at this conference. Apparently it's not the case. So let me say in a few words what he did. In this very recent paper, he derived the radiation reaction part of the scattering angle in GR using a very smart shortcut. He used the previous result with Donato Bini relating radiation reaction to the loss of energy and angular momentum, and he argued that at 3 p.m. level, only the latter, the angular momentum loss, enters. He computed it to order g square, and from that he got the 3 p.m. radiation reaction correction to the Bern-et-al. Deflection angle, recovering smoothness and the ACV ultra-relativistic limit, all in GR, not n equal 8. Now, our method provides instead the radiation reaction correction to the eikonal phase real delta 2, not directly to the angle, but directly to the eikonal, from the zero frequency limit of the energy loss at order g cube. So it's quite amusing that, what we got as energy loss at order g cube gives precisely the same result as radiated angular momentum at order g squared. We understood mathematically why the two calculations lead the same results, but the physical interpretation looked to be different. And here I flash the result for GR, which agrees completely with what Thibaut Damour was writing, only written in terms of delta 2, because this is what we get directly from the eikonal. Here you have the Bern-et-al. Result in this line, and this is the 2.5 PN contribution, which fits completely with what Damour has, but it's gotten from this zero frequency limit of radiation. And you can see that all these little numbers add up precisely to 16 sigma square at high energy, whereas the log S cancel nicely. There is a log S in this arc cosh. They cancel nicely at high energy, and you repeat the result. And the final slide is that we can also check the n equal 8 supergravity radiation reaction from the soft limit of radiation energy. Now, the final result is simpler in n equal 8 than in n equals 0, but the calculation of the energy loss is more complicated because in GR you only radiate gravitons, whereas in n equal 8 you can radiate a graviton, a dilaton, and because of our construction, also two vectors and two scalars. And they all add up to reproduce the correct radiation reaction term computed in the previous slides. And you see that it's a rather complicated cancellation of different terms, which lead finally to the good result. Summarizing, we have seen how the inclusion of the full soft region allows for the eikonal phase and the physical scattering angle, including radiation reaction terms, to be continuous functions of P over M, so from 0 to infinity, so that Newtonian and ultra-relativistic classical limits get smoothly connected. In other words, they meet. We have uncovered via analyticity an intriguing relation between the radiation reaction terms and the order G cube zero frequency limit of the omega spectrum, which is itself controlled by the soft theorems. This looks to be mathematically equivalent to Damour's recent connection between radiation reaction and radiated angular momentum at order G square, but the precise physical reason for the equivalence remains to be understood. And I want to conclude with something I said at Amplitudes in 2019 in Dublin. I was concluding with the following sentence, that eventually one would like to extend these results, which were about radiation, to arbitrary masses and kinematics, and to combine them with recent ones on the conservative gravitational potential at 3 p.m. level, leading hopefully to a full understanding of gravitational scattering and radiation at 3 p.m. level. And I think in the year and a half that elapsed since then, we have made quite a lot of progress. So I'm very optimistic. Thank you.
Okay, thank you very much. So because we would like to keep the schedule on time, if you want to take a break right now, you can, but we're also taking questions now. So there's time for a few questions. We'll try to reconvene by the hour. So Julio, please.
Hi, Gabriele. Thanks for a nice talk. I just wanted to ask, the result that you showed for the real part of the phase in GR, is this as derived from the Moore's result, or is this a new calculation that you guys did?
That result, this one.
Yeah.
This one we got simply by applying to the case of gravity this relation. Namely, we have seen that there is this intimate connection between this analyticity argument between the imaginary part of delta 2 and the real part and the radiation reaction contribution to real delta 2, because this is all odd PN, half integer PN order. So we simply use that. Now the point is we know how to compute this 1/epsilon contribution to the imaginary part, because this is completely controlled by the soft theorems. So we don't have to go through the whole calculation of two loops. We only have, it's enough to restrict our attention to the 3-particle cut in the limit in which the emitted graviton is soft. For that, we use Weinberg's leading formula. The only tricky point is that we have to go to B space, whereas Weinberg is in momentum space. And once you do that, that's what you can get both the n equal 8 and the n equals 0. And actually, the n equals 0 is simpler than the n equal 8 because it's only one contribution. And if you look at this term, at this term you see is the same here. It's the same term that you find at in n equal 8. The graviton contribution is very similar. The only difference is that the 3-level diagram is slightly different, as you know, for n equal 8 because of the dilaton than for n equals 0. And it's very natural that that prefactor comes squared, because the soft theorem of Weinberg tells you that you have to take the 3 amplitude and multiply by this universal Weinberg factor. So then you have to take the square, and so that's how the square comes about. In Thibaut d'Amour's way, it comes in a slightly different way, but he also has this this fact. I don't know if it's clear.
Yeah, I'm just a bit amazed by the fact that then, if I understood correctly, this means that the H diagram that we always worry about does not play a role in this piece. Because
okay, guys, sorry. Sorry. I have
no,
to
the
jump in.
will play a role, but it, because we go to the, you say because we go to the soft limit.